hearts on this slide too. It is still Valentine's Day. So, okay. I didn't mention this actually in steel design, or in concrete design. I had it on the slide. I didn't even mention it. Engineering Career Day is next Wednesday. So there might be a couple of you in here that actually came to it when you were in high school. We have a big event which takes place each year in February, and we invite a bunch of high school sophomores from around the area that are interested in engineering to come to campus. We're going to have like 130 kids here. In all honesty, if you're interested, I could probably use a little bit of help just manning the event and whatnot. Now, for you in steel design, you have a celebration on Wednesday, so you couldn't do the second part of the volunteering, but the first part, we could use some folks just helping with the registration. It's well before the exam here. If you're interested, let me know. If you're not interested in that, that's fine, but there is a SAME Youth Social event, which is taking place at Fat Patty's Tuesday night. You all should have gotten an email. Did you? I sent an email to Lee to have that forwarded out. Maybe she hadn't gotten a chance to do that. It's on Tuesday night. It starts at 5 p.m. It's the day before Engineering Career Day. It takes place over at Fat Patty's, and they're paying for appetizers, so let me explain. There is an opportunity for you to network with potential employers, and there's free food. That should be all that needs to be said if you're a college student, right? Free food and jobs. So it starts at 5 p.m. at Fat Patty's. They definitely like to see you there. Next Wednesday, we celebrate. Monday, come prepared to ask questions on the exam. The exam will cover lateral loads, it will cover tension members, yielding, fracture, block shear, it will cover analysis, it will cover design, it will cover threaded rods, no bolted connections. That's the first exam. You have a homework due on Monday. I'm going to give you the solution. I mean, y'all had me for class before, you know how I operate. I'm going to give you the solution on Monday. So what does that mean? I can't really accept late homework on the homework on Monday because you'll have the solution. So I do need that homework. Speaking of the homework, it's due Monday. This is the last class before it's due. Any questions on that homework assignment? Because you're almost done with it, right? Do I believe that? Have you started it? Some of you just looked like straight. And, no, you didn't look straight. You went like this. I saw that. Good luck. No, it's not. It really isn't that bad. It's like homework 2 in concrete design. That was a big assignment. This one, sort of in the middle. But yeah, it's due Monday. So, any questions? Okay. All right. So we're going to talk about bolted connections. Again, we're going to keep trucking with that. We're doing pretty good on schedule too. We might be a tad behind, but I trimmed some fat out of the later part of the course, so we've definitely got a little bit of wiggle room here. Okay, let's go to that. That's a good place. Okay, so we've been talking, we started talking about bolted connections last time, and so there are 2 types of connections that we will assess in this course. That's bolted connections and welded connections. I'd argue of the topics that we cover in this class, bolted connections are probably the second easiest topic that we cover, the first easiest topic being welded connections. Now, let me qualify that statement. There's a lot of information and like behavior stuff that you need to understand, but the math is really simple, okay? Basically, you're going to have a connection. There's 100 kips on it. Each bolt can hold up 10 kips. How many bolts do you need? 100 kip, 10, right? That's it. I'm being serious. It really is about that simple. There are some spacing limits and whatnot that you need. And we'll talk a lot about that stuff today. But I mean, that's basically it. All right. Now, in order to design a bolted connection or to analyze a bolted connection, if you're looking at a bearing type connection, there's 2 limit states. We're looking at the failure of the bolt and the failure of the plate. So let's really quickly recap the failure of the bolt. The bolt shear capacity, the load required to shear the bolt in half. So the capacity is the nominal shear capacity, the FNB times the area of the bolt being pi d squared over 4. When you're looking at FNB, your nominal shear capacity, it's a function of whether or not threads are included in the shear plane. If threads are included, the bolt's going to be weaker, okay? So when you look up FNB values in table J3.2, it actually says, okay, group A bolts where the threads are not excluded from the shear planes and group A bolts where they are excluded. And so in this course, we will refer to that as group A in, threads being excluded, and group A X, group A and the threads being included, group A X, threads being excluded. Remember, group A, there's no such thing as a group A bolt. That's just us taking a bunch of different types of bolts that all have the same behavior and saying, okay, they're group A. But there's no such thing as a group A bolt. There are A325 bolts, and so on and so forth. Now, the other thing that you have to ask is the bolt area. I didn't lie, the area of the bolt is pi d squared over 4, but that is assuming that you have a single shear plane. So a bolt tying 2 plates together. But if you have something like a splice where you have a bolt going through 3 plates, well, there's 2 shear planes there. So you have to multiply the area, if you will, by 2. It's not, the bolt isn't magically twice as strong, but you have to shear through twice as much area to separate the bolt from itself. Now, everything I'm talking about is pretty much nil because you don't have to compute the capacity of a single bolt. But you don't have to do that at all. All you have to do is look at the table. It does all the math for you. We can walk through this together. Let's do one super quick, just so you see where these numbers are coming from. So watch this. Let's just keep it simple. All right. So we'll say group A. We'll say the threads are included. We'll say the bolt diameter is 3/4 of an inch, and we'll say single shear. All right, so FNB, if I have group A and I have the threads included, is it 54 or is it 68? Well, think about the concept. If the threads are included, would the capacity, the nominal shear capacity be 54 KSI or 68 KSI? 54. It'd be 54. The threads are included, the bolt's weaker, right? And this is, again, from table J3.2. So FNB is 54 KSI. And so, remember our phi value is 0.75. Therefore, the capacity of a single bolt would be phi FNB times AB. And we multiply that by 1 because it's single shear. So 0.75, 54 KSI, pi over 4, 3/4 squared times 1. Somebody do that and tell me what that is. So 17.9, something like that. Got a second on. So that's 17.9 kips. I'm going to say kip per bolt, right? Whereas if you go to this table in the spec, all right, what do we have? Let's follow this through, right? So 3/4 inch diameter bolt, group A, threads included, single shear, right on the money. This just does all that for you. So you don't need to do this, but I just want you to see where these values are coming from. It's really not that complicated. So if I have a connection that uses these types of bolts, and there's 8 bolts, what's the capacity in block shear, or in bolt shear? That times 8. Pretty simple, right? Bless you. Any questions? Let's say this one's easy. If there's anything that's difficult, I would say it's probably the bolt bearing check, which we're going to talk about now, but is everybody good on this? All right, let's talk about bolt bearing, okay? So what I've got is a plate, I've got a bolt hole, and I'm yanking, right? And so if I'm yanking, and I'm drawing this in an exaggerated fashion, I'm going to have my bolt actually, in contact with the plate right here, right? So it's one of those things where you're applying the load and it's like, what's going to give? Well, either the bolt's going to snap or the plate's going to fail. So let's talk about failure of the plate. We call this a bearing failure, okay? Now, and we say bearing failure because the bolt is literally bearing on the plate, okay? Now, hence why we call this a bearing type connection. Now, there's two ways that the bolt can fail, okay? The first is what's called tear out. So it's kind of similar to like a fracture or a block shear type failure. Like you're literally shearing that out, okay? And so it actually looks like you're ripping a chunk out of the plate. Whereas ovalization, it's sort of like you're stretching the hole out. So this is where the bolt was into contact with the plate and sort of mashes up like Play-Doh. And so that's the steel yielding in a localized fashion right there at that connection. Okay? Now, the way that you compute the capacity is using this equation. Okay? Now, first off, before I start explaining this and going through this, let's recall a couple things. When you have an equation that's a pile of junk less than or equal to a pile of junk, what does that mean?
Minimum.
What's that?
Taking the minimum of the two.
The minimum, exactly right. Okay, so I will go ahead and tell you that what this equation is doing is saying this is the tear out component and this is the ovalization component. So basically what you're doing is you're saying, okay, here's the load required to tear that bolt out, or tear that plate out. Here's the load required to ovalize the bolt hole. The capacity of that plate right there is just the minimum of those two, okay? And if you're wondering, like, well, Dr. Mike, how do you know? You're going to see how I know that one's tear out and one's ovalization very, very quickly, okay? Now, I got a little box over there on the bottom right that says, for this computation, we are considering deformation at the service load. Dr. Mike, what the heck are you talking about? Well, maybe that involves us turning to section J3.10 on page 16.1-135, and let's actually see what I'm talking about. Because everybody brought with them their AISC 15th edition steel construction manual. Actually, hey, everybody did. I like that. That's what I like to see. Okay, so we're in chapter J, so you're back here, you're going to be back here. All right, we're in chapter J, and we're in connection land. Now, if you look here, the way chapter J is organized, J1 is your intro, J2 is welds, J3 is bolts. So that's why we're in J3. So for the next few lectures, we're going to be in J3 for a bit. And so if you look at the various sections within J3, like if you're looking at this page right now, you should see like J3.8, which is slip critical connections. J3.9, combined tension shear and slip critical connections. And we're on J3.10, which is bearing and tear out strength at bolt holes. So that's what we're on right now. And so it starts on 135, but then it also continues into the next page. So it tells us that phi is 0.75, which, there we go. Now, if you turn the page, right here where it says bearing and tear out, notice how it's split up into when deformation is a design consideration and when deformation is not a design consideration. So what that means is this, okay? Remember there is a difference between factored loads and service loads. Service loads are the loads that, quote unquote, are actually there. They're the ones that are actually on the connection. And then we take those loads and adjust them by, increasing them with, 1.2 dead and 1.6 live. We adjust them with these load factors to account for probabilities of failure. So there is a difference between what we're designing for and what's actually going on. So again, just because you put 100 kips of live load on there doesn't mean that you're designing for 100 kips. You might be designing for 160 kips. Okay, so under the service load, What this is saying to the engineer is, okay, you have a choice. You could design this connection and you could want deformation at the service load to be a design consideration or not. So what that means is under the actual load that's applying, do you want to see these deformations? Now, Greg, this guy right here, does not. I want to consider deformation of the service load. I don't want any of those ovalizations or tear outs starting at all. So whenever I design bolt bearing connections, I always consider the deformation to be a service or to be a design consideration. So if you don't care, so for instance, let's take bolt bearing. So it says 2.4 DTFU. When deformation is not a design consideration, the capacity is a little bit larger. So in other words, if you don't care about the bolt stretching or the bolt hole stretching out a bit, you can assume that connection has a larger capacity. I do care. I don't want that to happen. So I always consider that a design consideration. Okay? Does that make sense? Yes, sir.
When would you choose the other one?
That's a great question.
What's the point of having it?
Well, it depends on that's a great question. I think the best answer is it depends on the structure that you're designing. There's a big difference between designing a office building that's going to have people in it and a grain silo storage where who cares? And I understand, and I can appreciate that. So I think the best answer would be it would depend. But honestly, even for me, I would probably still do it. So that's a great question. All right. Are there any other questions? This is great stuff.
So by that, you're saying you'd rather use the 3.0?
No, I'm saying I'm using the other one. So look at what this is reporting. This is reporting capacities, okay?
Mm-hmm.
What it's saying is if you care about the deformation, then the capacity is lower. But if you don't care if it stretches out a bit, then you're able to bump that capacity up a bit. I don't want that. I want to assume the worst case scenario. Remember, what this is reporting are capacities. So the more conservative option would be to use the lower value.
Oh, yeah.
Does that make sense?
Yes, I get that.
So when it means when we're talking about conservative designs, like when in doubt, use the conservative option. For capacities, that means the lower value. For loads, it's the higher value. Does that make sense? That's good stuff. Now, I said earlier that I'd be able to look at this and see which one's ovalization or bearing and which one's tear out. Well, I mean, obviously it's organized like this in the spec, but there's another way that you can discern which equation is for bearing and which equation is for tear out, and that's to actually look at the expressions. Okay, so let's look at this right here. So there are some terms here that you probably recognize and some that you don't, okay? So for instance, we know what T is, that's the plate thickness. So it says T, but it depends on what we're talking about. So if we have bolts going through the flange, we would use the flange thickness or the web thickness. It's whatever the thickness of the plate that we're going through. Okay, so that's why it just says T, but for us, that could be TW, it could be TF, it could be anything. The bolt diameter, I actually added the D sub B, because this just says D in the spec, but I added D sub B because I want it to be clear that that's the bolt diameter. FU is the tensile stress of the plate, but there's this new term here, this L sub C. That one's new, okay? So what is L sub C? L sub C is defined as the clear distance between plate material. Now, the spec gives you a little bit of a longer word salad definition, and I'm going to explain that. Now, so just like before, we can take that and we can split it up into the minimum of these quantities. Now, I'm going to take this equation and make it a little easier here in a second. But basically, the upper part relates to bolt tear out, the lower part relates to bolt hole ovalization or bolt bearing, and here's why. Okay, now let's talk about LC. LC is the clear distance between the edge of the hole and the edge of the plate or the edge of the adjacent hole. Okay, so I'm going to look at this plate right here. So I'm taking this and I'm yanking on it. So remember before when we used the letter S? Remember, S was the distance between bolts along the direction of the load, right? So if I was talking about this distance, what would I use? Like if I had another bolt over here, I'd call that the gauge distance. I call that G. I heard somebody say G. All right. So that's the longitudinal bolt spacing. This is the edge distance. I'm going to call that L sub E. So S is the center to center bolt spacing here. LE is the distance from the edge, or from the center here to the edge. Okay, that's LE. The LC values are basically the clear distance from plate to plate, from edge of plate to edge of plate, or from edge of plate to edge of plate. So as a result, we actually have two LC values that we need to consider. An LC for the bolts on the inside of the connection, and an LC for bolts on the edge of the connections. That's why I have an LCE and an LCI. And how would I compute that? Well, this one right here, I would take the edge distance and I would subtract half a hole diameter, right? For this one, subtract half and half, so subtract a hole diameter. Does that make sense? So the math is pretty easy, okay? Sound good? Now, what's going on with this check? Well, if you look at the 1.2 LCTFU, what we're doing with that, remember I said that's tear out? It's kind of like a mini block shear check. So if I was yanking at this, I basically assume that this is a block shear failure. And if it's a block shear failure, what would be my area in shear? Well, it would be the length times the thickness, right? But what do you do with shear? What's that magic number that always pops up with shear? 0.6. Remember I told you there'd always be a 0.6 associated with shear. Well, I take this length times this thickness times 0.6 times 2, because there's one here and there's one there. What's 2 times 0.6? 1.2. So that's sort of another way that you can tell that this is the tear out expression, because it's a mini block shear check, basically. All right. So that's why we have the 1.2, because it's sort of a 0.6 in disguise. Sound good? So this one you can derive, this one you can't. This is sort of empirical. This is going down to the lab, ripping a bunch of plates and figuring out a simple expression that works. So remember in steel design we have the difference between mechanistic equations that we can derive and empirical expressions that we just go down to the lab and break some stuff and find an equation that fits. So that's what that expression is. Does that make sense? All right, so what I can do is I can take this, I can retool this expression and come up with something a little bit easier, and that's the one that we're going to use. But before we move on, y'all don't like me very much. In tension members, to calculate the hole die area, we take the diameter of the bolt, and what did we add? 1/8 of an inch. We're not talking about tension members right now. We're talking about the actual connection, the physical dimension of that hole. We're actually talking about the physical hole itself. Why did we add 1/8 of an inch? We added a 1/16 for the erection tolerance. We actually drill the hole larger. So the bowl itself, the hole itself is physically 1/16 of an inch larger. But we added that additional 1/16 to account for the fact that we didn't think that little bit of lip of material around the hole could transfer load to the member. But we're not looking at the member. We're looking at the actual hole. So here, when we do hole diameters, we add 1/16 of an inch, not 1/8 of an inch. Okay? I apologize, but it sort of is what it is. Somebody's going to mess that up. And you're like, Dr. Mike, that's understandable. That's easy to confuse. I'm like, I know. So are you still taking points off? Yeah. All right, and then last, what I did here from this here, I just took this and factored out all the common stuff. So you can just compare LC and 2 bolt diameters and figure out which one you need to compute. Questions? Okay. Now, for connections, there are capacity checks, but there's also other things that you need to assess. Like, remember with tension members, we had the gross section yielding capacity, we had the net section fracture capacity, the block shear, but there was something else. We also had to check slenderness, right? Because it didn't matter whether or not the connection had adequate strength, there was still this service check to make sure that the member wasn't too slender. And why did we place a slenderness limit on a tension member? We did that so that we could construct it. It had nothing to do with how strong the member was. It was to ease construction. It was a different type of check. Well, there are different checks associated with bolted connections, basically related to how they are laid out. Okay? Now, there are two things we have to look at: how far apart the bolts are from each other, and how far apart the bolts are from the edges of the plate. Okay, so let's talk about why. What do you think would happen if bolts got too close together? Why is that a concern? Why is it a concern if I'm designing a connection? What happens if the bolts get too close together? And I don't want you to think about capacity or calculations. I'm not talking about that. I'm talking about real life. What's the problem with the bolts getting too close together?
Like weaker because there's less material in between.
I'm not talking about capacity. That is an issue, because if you have just like this little lip of material, that's an issue. I'm thinking going down to the garage with a wrench. What's the problem if the bolts get too close together?
It's harder to pedal.
It's hard to get a wrench around them and actually tighten them up, right? You have to have at least some minimum spacing between them so you can actually get a wrench around them and tighten them, right? Like, that's what I'm talking about. I'm talking about practicality, right? So you actually need some space between the bolts so that you can facilitate construction, actually putting it together, right? So there's some space. Now, let's look at the flip side. What would happen if the bolts get too far apart? All right, I'll take the bolts and make them 12 inches apart. What's the problem there? Anybody?
Are we still talking practical stuff?
Yes. Nothing with math, or I'm not talking about math.
So if you're up in the air putting them together, you have to move your own method.
That's not going to be it. But as long as you get two bolts in the member, it's probably not going to go anywhere.
Yeah.
When you're constructing, according to Ocean one, there's a common rule called the 2-bolt rule, that if you have a member, as long as you get 2 bolts in on each connection, then the crane can let go. And that really wouldn't matter depending upon how far apart the bolts are from each other. But you were about to say something.
You have to, like, if they're really far apart, you would have to, like, move to install the other one? Is that?
No. Let me ask you this. All right. What are bolts doing to member A and member B? I mean, if I have a bolt through them and I start tightening that bolt, what happens to these two plates, right? We got a plate here, stick a bolt, start tightening the bolt. What happens to the plate? They come together, right? Now, what happens if the bolts get very, very far apart? Well, maybe you got that going on. There's a little bit of gap between them. Who cares about that? Why is that wrong? Why do we care about a gap being between the plates?
Wouldn't it allow the materials to get into water whenever it's raining or something, so it rusts? And...
He just said the magic word. The magic word is water. If the bolts get too far apart, you can get water in between your plates. And metal rusts. That's a bad deal, right? So, I skipped away from this slide for a reason. Okay, we have bolt spacing requirements and bolt edge distance requirements for 2 reasons. If the bolts get too close together, it becomes difficult to actually construct the component. But if they get too far apart, you can get water in between them. And so why do we have bolt spacing and edge distance requirements? To facilitate construction and to prevent corrosion, okay? And when you start looking at the limits that we use and why we pick what we do, that'll make a lot of sense, okay? So let's start going through the specs. So now we're really going to start digging into Chapter 3. So I want to go back, let's actually go back to the very, very beginning of Chapter 3, okay? Or sorry, J3. So let's go to, I know this says 16.1-130. Let's turn to 16.1-126. I want you to kind of actually get your teeth sunk into what it's like to go through some of these specifications. I want you to become a bit familiar with this, all right? So I'm on 16.1-126, and we're looking at section J3. So this is looking at bolts and threaded parts, okay? Now, I'm going to tell you, by the time we're done with this, we'll probably have looked at just about every section in this. So, okay, section J3.1 is talking about just the bolts themselves. What is Group A, Group B, and Group C? It's talking about bolt pre-tensioning. which will become clear later on when we look at slip critical connections. But, from there, we can really sort of move on. If you turn the page and you go to page 2, we're in size and uses of holes, okay? Now there's a lot of text going to describe this, but if you actually turn the page to J3.3, J3.3 is really sort of what we're after from a hole size standpoint. I actually want to look at J3.3 just for the heck of it. That table. So it says table J3.3 nominal hole dimensions. Look how if you have a half-inch hole, the standard hole is 9/16, 5/8, 11/16, 3/4, 13/16. There's a pattern, right? The hole diameter is 1/16 of an inch larger than the bolt diameter. Remember I told you how we actually drill the hole physically larger for standard size holes? There you go. What about oversized holes? What about slotted holes and things like that? There's all of your appropriate dimensions. And then there's other text in the size and use of holes for when you would use oversized holes, when you would use short holes or long slotted holes, and so on and so forth. Then when you start getting into section 3, minimum spacing, minimum edge distance, does everybody see what we're talking about here? Okay, I'm on the bottom of 16.1-130, and so you should see what's on the slide there. You should see that on the bottom of this page. What does it say? The distance between standard, oversized, or slotted holes shall not be less than 2 2/3 times the bolt diameter. However, the clear distance shall not be between bolt holes or slots shall not be less than D. Okay, and then it also says a user note the distance between centers of holes of 3D is preferred. Okay, so what that's saying is the minimum spacing is 2 2/3 times the bolt diameter, preferred spacing of 3 times the bolt diameter. And again, the reason for that is if they get closer, you actually can't tighten them. The bolt heads will start knocking into one another. You can't get a wrench around them. So that's the reason for that limit. Okay? All right? So that's the minimum spacing requirement. We can just compute it. 2 2/3 times the bolt diameter. If the spacing is less than that, we got to start redesigning our connection. Speaking of when we design the connection, so for example, remember how I said there's 100 kips on the connection? There's 10 kips per, each bolt can hold up 10 kips, so I need 10 bolts. How do I lay them out? Well, make sure that they're not 2 2/3 times the bolt diameter closer together than one another, right? Figure out how to space them. What about the edge distance? If you read what it says here for the minimum edge distance, the distance from the center of a standard hole to an edge of a connected part in any direction shall not be less than either the value specified in table J3.4. Now, minimum edge distances come from fabricator preferences. So remember, what are we talking about here? We're talking about drilling holes in plates, right? So what you see here in table J3.4, I mean, there's a pattern. It's pretty much the diameter plus a 1/4 of an inch, but not always. Like if you look at the bolt diameter for 1 1/8 of an inch, it's actually 1 1/2. Does everybody see that? So where this is coming from is this. So look at this. Here's a plate, right? And I got to drill a hole on the edge of that plate. How close do I get to the edge of the plate where I'm like, I kind of need to get back that off a bit? Where's the closest that I can drill that hole to the edge of the plate and be comfortable that the plate isn't going to get tore up or I'm not going to crack through the plate or anything like that? These minimum edge distances really come from the fabricator. That's the fabricator saying, okay, that's about how close I will put that drill bit towards the edge of the plate before I stop feeling comfortable that the hole is going to, come out the way I want it. All right, does that make sense? Yes, sir.
Is that not dependent on the type of steel you're using?
That's a great question, and I would give you a different answer. I would say it's not really so much dependent on the type of steel that you're using, more than it's dependent on the type of drilling method that you're using. In other words, are you drilling? Are you sub-punching? Are you using a CNC to water cut or laser cut it or plasma cut? I mean, you know what I'm talking about? I would say that's probably what the fabricator is going to think more about than the grade. But you could, if you wanted, you could go to the fabricators and start collecting this information and say, okay, if you're drilling here's your minimum edge distances. If it's a CNC, here's your minimum edge distances. But from a designer's perspective, this is probably good enough just to come up with something to lay out the connection. Does that make sense? But that's a great question. From the grade standpoint, I actually don't really think it would matter all that much. I mean, maybe you just have to put a little bit more oomph into the drilling or something like that. But I really don't think that that it would affect the overall fabricator's preferences on the edge distance. I think that's a really good question. Yes, sir.
What about like staggered distance? Is it the same way?
That's a great question. When you have a staggered connection, the way these bolts are, or the way these limits are arranged, is how far the bolts are from the edge and how far apart the bolts are from each other. It doesn't matter if you have them lined up in a grid or a staggered pattern or whatnot, as long as the center of this bolt and the center of this bolt has a spacing at least greater than or equal to 2 2/3 times the bolt diameter. And it doesn't really matter if it's staggered or not. It's a great question. We're going to limit our bolted connection discussion to grid patterns. But if you were designing a staggered connection, there's nothing to say you couldn't. Just make sure that you maintain that for all of the bolts in the connection. Because again, the purpose is just to make sure you can tighten it up. And think, the guy out there with the wrench doesn't really care whether or not you designed it as a staggered connection or not. They just want to make sure they can tighten it up. You know, that's a great question. Everybody else, did that make sense? Any other questions? All right. For the maximum spacing, now check this out. Remember, minimum distances are for fabricator preference and construction. Maximum spacing and edge distance requirements are for corrosion, right? So if you read section J35, look at the verbiage. So if you look at it, there is a difference between, so for instance, let's look at this second sentence. The longitudinal spacing of fasteners between elements consisting of a plate and a shape or two plates in continuous contact shall be as follows. For painted members, the maximum spacing is 24 times the thickness or 12 inches. But for unpainted members, it's 14 times the thickness or 7 inches. Okay? Now, if you digest that and you think about that for a bit, what the spec is saying is that if you have a member and you painted it, you can get by with spacing your bolts out a little further. But remember what the limit is for. The limit is for preventing corrosion, right? Well, if your member is painted, it's okay if the bolts are spaced out a little bit further, because what happens if water gets in between them? The water's not in contact with the steel, it's hitting the paint, right? So if you provide a system like painting to prevent corrosion, then you can get by with a little bit more water, or a little bit more space in your bolts. Now let me be clear. Most designers in load carrying capacity connection situations are not going to try and bump up against maximum spacing limits. Usually we try and keep our connections small and keep them compact. But if that's a situation, your maximum limit depends on your coating. What we do in this class is we assume the worst case scenario. So we go with spacing requirements assuming the members are unpainted. So we go with unpainted considerations. But if you have a painted member, just recognize that. Now your edge distance requirement doesn't matter whether it's painted or not. If you read this first sentence, the maximum distance from the center of any bolt to the nearest edge shall be 12 times the thickness or 6 inches. It doesn't care whether or not it's painted or unpainted. It doesn't matter. Sound good? All right. So I put here on slide 172, I put a nice little summary of all the formulas. So here we got. So we have a bearing type connection. We have two limit states to consider. We have bolt shear. We have bolt bearing. Bolt shear, I can look it up. Bolt bearing, the capacity of a single bolt is 1.2 times the thickness times FU times the minimum of either LC or 2 times the bolt diameter. And whichever one of those is the minimum will tell you whether or not the bolt is going to tear out or the bolt is going to oval, or bolt hole is going to ovalize. How do I compute the LC values? Well, the LC values, there's a different LC value for the edge bolt than there is for the interior bolt. And then all of that is based on a hole diameter, where the bolt diameter, you add a 1/16 of an inch, not an 1/8 of an inch, because you're looking at the actual physical dimensions of the hole and not how much will transfer load to the connection as a whole. Okay? As a whole. Connection as a whole. That was pretty bad. It's okay. Lastly, so bolt spacing requirements. The minimum bolt spacing requirement is 2 2/3 times the bolt diameter, and the preferred spacing is 3 times the bolt diameter. The maximum bolt spacing is 14 times the thickness, or 7 inches, assuming unpainted steel. A very, very common bolt pattern is to put your bolts 3 inches on center. 3 inches on center, most fabricators are already tooled to do 3-inch on center connections, because 3 inches on center meets the requirements for 3/4 inch diameter bolts, 7/8 inch diameter bolts, and 1 inch diameter bolts. And those are the 3 most common bolt diameters that we use in structural engineering. For the minimum edge distance comes from a table. For edge distances, the minimum comes from a table. The maximum is 12 times the thickness, or 6 inches, regardless of painted or unpainted. So I guess maybe a note here is that this one right here, that one assumes paint or unpainted steel. So, but we're always going to assume that in here. It's the most stringent assumption. Sound good? All right, this is what we're going to do next time, because I threw a lot of stuff at you. We're going to do an assessment of this connection, and we're going to look at this. Basically, we're looking at this center plate. We can look at the splice plates later, but we're going to look at the center plate. We're going to see what's the capacity of that connection. Now, if you understand how to compute the capacity, you can then do design, and then we're going to design a connection. So you can see how there's nothing there. We're going to design that connection later on. I'm going to actually call it there, but one thing I'll do, I'll leave it up here in case you all want to denote that. But slide 172 and 173 are sort of my summary for you for bolted connections. With this class, there's a lot of different tables and formulas and equations, and I always like to put these little, breather slides, if you will, like, look, here's everything, Sound good? Happy Valentine's Day, everybody. That's all I got.